The recording is on, and thank you everyone for coming. Very happy to see you all here. And this week we're doing the presentation on TD3, the paper about addressing function approximation error in actor-critic methods. So I'm going to post the link in the Slack chat in the Slack channel. By the way, have all of you read this paper?
Yes.
Yes. Nice, nice. Excellent. How do you guys feel about the paper? Difficult, easy compared to the
Difficult.
papers? Difficult, okay. Um,
And compared to DDPG, for example.
okay. Interesting. For me personally, I actually found it quite easy. Not easy, but it's very intuitive to read. The authors spend a lot of time trying to give intuitions about why they do certain things. And it's very intuitive. You just have to spend a little time to read it. But let's see if during this presentation, maybe I think I have a kind of a good understanding of it. Let's see if I can help you understand it, or and if obviously I could be wrong, and feel free to ask questions and jump in to discuss with me. So first of all, there's something that I've been doing is to use Mendeley to manage my all of the literatures that I read. And with Mendeley, you can add highlights, which I found to be a very effective way to help me learn, understand what's going on. And here is a annotated PDFs with a bunch of colors and highlights and stuff. And I use different colors for different things. Like purple means it's important tricks and details. Yellow means it's just general emphasis. Orange means it's important assumptions. Pink means intuitive, plausible inference, which might not be true, but it's like something like saying target network will help the agent train. It's more like a plausible explanation and inference, but maybe it's not true. And blue means questions. So these have helped me greatly with reading papers, and I just include the annotated PDF as well in the slide. And let's do a really short recap on DDPG. So remember, DDPG is an algorithm that has the actor-critic setting, and you train the agent by first to minimize the critic loss, which is which is essentially the sum of squares between the Q value as well as the right, as well as the reward plus the Q value at the next time step. That's the fundamental Bellman equation that is used to train DQN. And it's just a very common technique to train the critic by doing this sort of temporal difference learning. On the other hand, the actor side, you're maximizing, you're finding an action that maximizes the Q value. That's what this all says. You're trying to find an action, this A, trying to find an A that maximizes this Q. And if you take a look at the implementation code, which apparently I need to open a new window for it. If you look at the code, the actor loss should be very straightforward. It should be just a Q network and then maximize the Q network. And then when you optimize over the actor, you're stepping over the actor. That is because you're using the actor to generate an action, and then only the actor optimizer optimate the actor loss, which means parameter of the Q network is not affected by the will not be modified by the actor optimizer. However, it'll find this line of code, which is the neural network parameter that will generate the action. It's going to find the action that maximizes the Q value. So that's how the actor is being maximized. Okay. And what is the problem? The problem is that, at least in our experiment, the DDPG just kind of its performance is rather unstable, and we run the benchmark, and a lot of them kind of crash. But you can see that a lot of them. So DDPG2 continuous action is with the batch normalization tricks. Among a bunch of normalization tricks. But as you can see, its performance it's not really improving steadily over time, but rather it oscillates. And the same thing would happen with pretty much every environment we see. Of course, this could be something that we didn't implement correctly on our side, but overall, our experiments kind of show that the DDPG is not really stable. The only environment that it seems to perform well on is pendulum. But even so, it's still not able to produce the exact performance as soft actor critic. It's still somewhat unstable. But anyway, so in this paper, TD3, it talks about what's the problem in DDPG. The problem is overestimation bias. And I highlight it here. What is overestimation bias? It is a property of Q-learning in which maximization of of a noisy value estimate induces a consistent overestimation. And notice this noise is unavoidable given an imprecision of the estimator. And this inaccuracy is further exaggerated by the nature of temporal difference learning. So as you can see here, how you do the critic loss, essentially what it's saying is that, first of all, this Q is inaccurate. And because every time you update the critic loss, you're using the temporal difference learning. So essentially, you're always having this sort of overestimation bias whenever you do a critic loss update. So that's why the problem becomes severe. And what's the impact? The impact is that due to overestimation bias, this accumulated error can cause arbitrarily bad states to be estimated as high value, resulting in suboptimal policy updates and divergent behavior. And to give you a sense of how bad is the overestimation bias, this is what it kind of looks like. So here you have DDPG and true DDPG. That's the color associated with the algorithm's run. And then on the y-axis is the average value. And on the x-axis is the time steps that is trained. So notice the average value of DDPG experienced significant variance. You can see the arrow bar is very wide, and that it's much more. It's definitely an overestimation compared to the true DDPG value estimates. And you might be wondering, how did you come up with the true DDPG? So the author mentions it. The true value is estimated using the average discounted returns over 1,000 episodes following the current policy, starting from states sampled from the replay buffer. So that basically means the true value is just saying, assuming they're just going to run the DDPG algorithm at the particular at that stages of training. I see. At that stages of training, and run it for 1,000 episodes to get its average value, to get its true value. So you can consider it as an evaluation of the policy. I actually run this policy for just many episodes, and I want to see its true value. So that's what the true DDPG is evaluated. And as you can see, the overestimation bias is there. Any question? Does this make sense?
Yes.
Okay. Um, and then here, which the CDQ, which I'll explain in later slides, is the proposed approach to help fight the overestimation bias. And as you can see, their proposed approach is much better in the sense that there's not so much of an overestimation. In fact, if you look closely over here, there's underestimation, right? And they claim that the underestimation is more favorable for a reason that the underestimation error won't be propagated by the temporal difference learning. Because here you see because the action that is being selected is usually the action with the maximum Q value. So if an action is being overestimated, it's going to be selected more and therefore appearing more in the temporal difference update. Therefore, the overestimation error will be propagated more than underestimation error because action that has been underestimated will not be selected as much. Therefore, its error won't be propagated by the temporal difference update. So that's their logic. And in addition, a couple things that they could help to battle the overestimation bias. Sorry, this slide is it's about a different thing. It's about how overestimation bias could affect policy update. So here we learn that there's an overestimation bias, and here we learn how overestimation bias affect the policy updates. So in this case, they compared two approaches. The first is to fix a policy, and then they use a target network to compare the average value, and then to see how fast they converge. And the simple story is basically if you have no target network at all, which is the tau equal to 1, then it learns very quickly. But its error, its variance will be larger. But if you use the tau of smaller value, it'll converge slowly, but it'll be more controlled and stable. So they suggest that in fixed policy, that's okay. However, in learned policy, that means you're using the value, you're using the Q value function to learn the actor, which is this part. You're doing the actor loss when you have an inaccurate Q value, then all of a sudden the variance becomes significant. As you can see, using tau equal to 0.1 doing the slow update, it's much, much more controlled than using the comparing doing harder updates with a target network. And using harder target network, they experience tremendous amount of volatility and variance. Now let's see what these two texts talk about. Right. While updating the value estimate without a target network, tau equal to 1 increased volatility, all update rates, which is a tau, result in similar convergent behavior when considering a fixed policy. So this is fine. However, when the policy is trained with the current value estimate, then use a fast updating rule, target network results in highly divergent behavior, which is this part. So essentially, yeah, if you're training your critics and the actor at the same time, then you really need to use a smaller tau value. Use the target network to help it to fight the overestimation bias. And then the author suggests if the target networks can be used to reduce the error over multiple updates and policy updates on high error rate states cause divergent behavior, then policy networks should be updated at a lower frequency than the value network to first minimize the error before introducing a policy update. So what this part is saying is that essentially, since the author kind of show that you want to do slower update with the target network, it's saying that with policies you should do it even at a lower frequency. You should slow everything down, which is kind of the intuition of the paper and what the name suggests. It's twin delay. The twin means the policy and the critics are both delayed in terms of its learning. They want the critics to converge before the policy update. And what's the proposed approach? The first approach is that the author suggests we should use a clipped double Q learning. So this, if some of you remember from the software actor critic paper, the clipped double Q learning, I think it's essentially what's being implemented in SAC as well. They're taking the minimum of 2 target Q network, and then as we mentioned earlier, while this update rule may induce an underestimation bias, this is far preferable to overestimation bias, as unlike overestimated actions, the value of underestimated actions will not be explicitly propagated through the policy updates. So they're essentially saying, yeah, overestimation, also sorry. They're essentially saying underestimated action is fine because its error won't be propagated. And as you can see over here, the result of the clip double Q learning performs much better. Its overestimation bias is significantly lower. And as we mentioned, it's even underestimating a little bit, which is good considered by the paper, right? And now, here is a complete proposed approach. So they first suggest that the use of a target network, a common approach in deep Q learning methods, are critical for variance reduction by reducing accumulation of errors. Second, to address the coupling of value and policy, we propose delaying policy updates until value estimate has converged. Finally, we introduced a novel regularization strategy where a SARSA style update bootstraps similar action estimates to further reduce variance. So what does that mean? The third technique. So the target network and the delaying of the policy updates is very intuitive. What is the third technique? The regularization strategy. So here it tells us the purple text tells us the motivation. Our approach enforces the notion that similar actions should have similar value, and they propose that fitting the value of a small area around the target action, where they generate an action and then they add a noise to that action that is clipped. And that noise is generated by a Gaussian distribution. So I think what they hope to achieve is that similar action, let's say 0.1 and 0.2, and then after adding the noise, they'll kind of look something like 0.15, 0.15, so that hopefully they'll produce the same value. And hopefully the neural network would be able to learn to deal with this noise to kind of normalize themselves into a certain range. It's like, yeah, I don't know how to kind of, does this part make sense? If you think about it, it's sort of like this, where imagine you have two actions that are supposed to be the same, should have the same value, right? But they're distant from each other, and then the value function could produce very different values. However, by introducing a Gaussian noise, you're essentially doing this, right? Such that they have a higher probability of being considered as the same action with the same value. So that's that part. And lastly, we have the performance, we have the entire pseudocode of TD3. So initialize CRIDA network, actor, all that, and they select an action with exploration noise, and store transition in a replay buffer. And then when they learn, they generate an action with the epsilon noise that has been mentioned. So this noise is different than the exploration noise. This is a Gaussian noise, a clipped Gaussian noise. And then they use the clipped double Q learning to set up the target. And then they update the Q network by using the target generated by the target network. And then here's a twin delay part. If T mod n, then we update the deterministic policy gradient as well as the target network. So that's a twin delayed update of TD3. And that's it. And then if you look at the performance, they basically achieve state-of-the-art results in every gym environments they tested. And overall, its training results is very stable. So yeah, state of the art. Any questions? That's basically the presentation.
Yeah, thank you.
My pleasure. Um, any comments or questions? Does everything make sense?
Oh, so a quick question here.
Yeah.
Regarding the, how did they call it? The target policy smoothing regularization, if I'm not mistaken. Basically, where they add the noise to the target, I think the slide before, yes.
Mm-hmm.
Since in the beginning they had this motivation to reduce overestimation bias,
Mm-hmm.
and this is basically by tweaking the target Q function.
Yes.
Right. Overestimation. And now that they add a noise to sample the target value,
Mm-hmm.
it doesn't ultimately defeats the purpose of reducing overestimation in the first place.
I don't think so. Because this part is really about, I guess, enforcing the notion that similar actions should have similar value, as sort of demonstrated by the little two circles here. You have a higher chance of being considered as the same value if you're different action but you're close together.
But even if you do that, this is the target Q function we are talking about. So how does it really impact the, for example, the actual Q value or even the actor network?
So that would be an interesting thing to study, right? When we do the implementation, we can take out the target policy smoothing regularization and see how it impacts. I actually didn't read that part in their paper where they talk about the ablation study. So what do they do? Actually, yeah, section 5.3. So they did do an ablation study. Where's the results? Okay.
I see. It kind of makes sense now.
Wait, so that's going to be the ablation study should be target TPS, right?
TPS, right?
Right. So without TPS, well, it performs better in ants, slightly better.
That doesn't really help much.
Yeah, it doesn't really help much. So it is an important technique, apparently.
I will be more interested in some curve focused on the TP aspect. Let's see if they have that. It does not. Oh.
Right.
There is one in the F section of the appendices, like the second figure 7, right?
Figure 7? Yes. So that will be the red curve right here. So yeah, it's sort of in the middle, I suppose. In Hopper, it's really not helping that much, but in Hafcheta, Walker, and Ants, I think the TD3 without target policy smoothing is okay.
In the spinning up docs, they say that you can reduce the scale of the noise of the training. So I guess they NBO the noise.
Okay.
Do you know if they're doing the same thing here, or if they're just keeping the exploration noise fixed throughout?
Wait,
this one.
So what noise did they anneal? Did they anneal the exploration noise or the target smoothing noise?
Target smoothing.
Okay, I see. Okay. Yeah, I mean, that's good as well, I suppose. But yeah, overall, I think it's a very intuitive paper, very well done, and their ablation study is spot on as well. I have to say this is actually one of the more preferable paper that I've read recently.
So the way how I see this algorithm, and if I can compare, for example, to PPO, which are of course a completely different family of algorithms, but what they have in common is that they put more and more constraint on the learning process, right?
Yes, a lot of even in the PPO implementation matters paper, a lot of what has been talked about is how you should do things slowly with policy gradient or deep learning, I guess in general. It's very easy to learn too fast, and then you stuck into suboptimal behaviors. All of these things that I've read recently with TD3, with PPL, it seems a lot of the techniques really focus on trying to learn things slowly. If you're being too aggressive with your updates, then you shouldn't do it, or at least you should wait.
Yeah, exactly. Because actually they try to solve more and more complex problems, right? And that's why it's more, it's more difficult. That's why the whole learning process should slow down.
Mm-hmm. Right. Yeah, and I think since for me it's very intuitive, and I think I can just kind of modify based on DDPG, and then just modify a few components to introduce the three things that has been mentioned in this paper. And the authors are also very nice enough to include their source code as well, apparently written in PyTorch. So what I would like to do is implement myself and implement the algorithm myself, and then compare it with the author's implementation as well as the spinning up implementation. Yeah, I think there's a very clear pathway to do the reproduction of this paper. Any questions or comments?
No, I think that's very intuitive introduction, and I like the fact that you also referring to the code. Because to be honest, it's sometimes much easier just to look at the code.
Right. Yeah, like some part of the paper is a little confusing. Like, for example, where they talk about proving the existence of the overestimation bias, which is this part, uh, and showed that the update induces overestimation in the value estimates, and it has a lot of equations. And the notation is a little bit confusing, and then I decided to use different colors to, like over here, when I was reading it, like the proof kind of starts with here. So this is why I use orange, because this is importance assumptions, and it didn't invoke a theorem or something. They just kind of say, as gradient direction is a local maximizer. I don't know what that even means. There exists an epsilon one sufficiently small, like these would require some sort of, like, how can you make these sort of these sort of assertions? Where's your theorem? Or, like, I guess this part is a theorem, but it's not explicit enough. But essentially, here a part is saying the pink is greater than red, and then blue is greater than uh, green. And then if certain condition happens, then overestimation could happen because pink is greater than green. Yeah, but this part I wouldn't read too much into it. The like formal proofs in RL is kind of, I don't know. It has its values, but they don't seem very useful, I suppose.
It seems like we almost always rely on approximations anyway. So
Yeah, it's like a lot of these formal proofs with approximations is, it's cool, but I don't know if they're actually useful. And they don't really provide.
guarantees.
Yeah, it's like saying if all of these happen, but it doesn't tell us about like the probability of this happening. Um, I don't know. The theoretical work could be improved, I feel like.
I said the paper though that the gradient is a first order estimate. It's just that when you're taking a gradient step relative to the first derivative, you're not utilizing anything about the curvature of space or
Mm-hmm.
like the Jacobian or Hessian or so on.
Yeah, I think that's the common issue, I suppose. I think if they want to take into the information of the curvature and all that into account, the whole auto differentiation package would have to, I don't know, maybe change significantly, something like that.
It'd be very computationally intensive. So
Mm-hmm. Yeah, for sure, for sure. But yeah, that's the paper. Yeah, I don't have anything else to say about this paper because it's. I think I cover most of it. I guess I can kind of talk about the plan after this paper. So I haven't been advertising the library for quite a while because I want to focus on try to get some of the more important algorithms out there, and then do this comprehensive benchmark, finish everything, and then sort of advertise and publish this library again. Um, Hopefully to get more people to use it and to have more people develop with it so that we can have a better library that is very hackable and usable by everyone. Uh, and my plan is after TD3, we would have implemented pretty much all of the major algorithms. And I think it would be a time to finish a lot of documentations, provide better support, and then just kind of try to advertise it again to get more people into it. Does anyone think about how TD3 might apply to discrete action space? It sounds like in discrete action space, it would be just queue learning, but with double clipped double queue learning as well as the delayed update, and that's it, right?
It should be possible to quickly apply the target the noise to the DQN, and you will probably get some DQN-TPS. But regarding the delayed update, since it's only the critic that is used, I am not sure it can be fine.
Wait,
not straightforward.
What's that?
The target policy smoothing should work on DQN, but since in DQN we do not have like the actor and the critic, there is nothing to delay the updates.
I think it. Oh, I see. Right, because there's not an actor, right?
You either update or you don't. So.
Right. Well, the actor in DQN is essentially choosing the action with a maximum Q value, right?
Yes.
Maybe we can do something like delaying that selection. So it's like you're using the previous Q network to sort of do the selection of selecting the action that maximizes the Q value. And then you're after T mod N, and then you update that Q value, update the Q value, and then you do the action selection again. Something like that.
I think that's already what they do by using the target Q network, because that one is slowly like following the actual Q network. So when
yes, you're right.
The max target Q, that's basically what they do.
Yeah, so you're right.
That can be done on top of this is maybe add some noise around the sampling of the action. But here again, since we do not have continuous action but discrete, the assumption that well, if you go back to the paper, we want the values of similar action to be almost equal, similarly valued. But since the action is discrete, I do not know if this assumption will hold on.
Yeah, there won't be this problem, right? Because actions are discrete. They're either the same or they're different.
Yes, so I am now thinking of how much do you want actions value to be similar? Because in this case, because of the discrete nature of the actions, well, they might represent totally different things. So
right.
Them to be close. This is also something we must maybe look more into.
Yeah, I don't know. It feels like the smoothing the noise. I have no idea how that's. I don't think it's even applicable to discrete action space because discrete actions are either 1, 2, 3, or 4. You couldn't just add like a epsilon to the action, you know.
But this action, maybe because it is sampled like using the argmax, so you can maybe take the second on the third one after the argmax. That kind of noise.
Yeah, I don't know. Yeah.
I'll fix this paper. There are some techniques for doing relaxation on discrete variables to get things like autodiff to work on them, so you don't have to always do hard max. This is one example of it. Other things might be more tricky, but to learn an embedding on the discrete actions.
I see.
Then there pick something.
Right. Well, yeah, definitely something to consider, but so far maybe no direct pathway to do so. But yeah, I think yeah. There's no much else that I know. I don't know. Any more questions or comments? Like, have you guys read the DDPG implementation by any chance? That's totally fine, but if you're interested in implementing TD3, definitely check it out. It's actually a rather straightforward algorithm. I would highly encourage you to give it a try, maybe, and see how you can go with it.
Since TD3 is kind of like a refinement over DDPG, does it make sense to just add the refinements directly into that implementation, or
yes,
is it worth it?
Yes, because it's based on DDPG, and the update rules in terms of like fundamentally how you update the critics and the actors are the same. So that's what I would do, is to add those optimizations, those tricks to DDPG, and just see if it gets a significant improvement. And if their paper is sound, it should. And assuming if my implementation is good too, I suppose.
I guess we aren't so interested in multi-agent stuff, but I did notice there's a multi-agent version of DDPG.
Beg your pardon?
I guess none of the benchmarks that we do are multi-agent, but
no.
I just stumbled across a multi-agent implementation like BBPG.
Really? That's interesting.
I put it in the chat.
Yeah, of course. And after TD3, which now I kind of expected to be implemented quicker, I suppose. It shouldn't. I don't think it's gonna take as long of a time. I mean, we should still take a month to sort of finish it. But after that, do you guys have any idea as to what papers to read, what kind of things to implement? I mean, when I was doing my independent study with the reinforcement learning, I do have a sort of a list, and a couple things that I think are interesting to read is distribution ORL, intrinsic motivation, transfer learning, and model-based RL. I don't know what kind of things do you guys have in mind?
I think a model-based will be an interesting tangent. But maybe before that, the distributional one, since we can directly apply it to DDPG and such.
I think this particular paper is maybe for the DQN or something like that, for discrete action space. But yeah, I think it's very interesting. I actually did a presentation on distribution RL. I didn't quite understand a lot of what it's trying to say, but some of the techniques that it's trying to do, it's very, very interesting. But yeah, I think, for example, intrinsic motivation would help with problems with very sparse rewards. If your research is related to any problems with sparse rewards, intrinsic motivation is it's definitely an interesting read. In model-based RL, this is currently the state of the art for one of the state of the art, I suppose. Yeah, definitely interesting.
Do you want to think about working on prioritize replay or hindsight replay?
Yeah, those are very interesting as well. Are those just different? What's it called? Replay buffer variations, or are they very different?
That's my understanding of them. They're just different ways of ranking trajectories in your replay buffer.
I see. Yeah, those things definitely will be interesting to explore as well. Priority experience replay buffer is one of the, I guess, earlier approach to help with DQN. Yeah. What else? By the way, with DDPG, there's kind of a problem with the implementation. Its training steps. It's taking so long to train. It takes 16 hours to train over 2 million time steps, and it seems that a lot of the time was spent on, I don't know. As soon as I turn on the weight and biases, it's kind of slowing everything down. Uh, I don't know what's causing it, but that's definitely something that I'll look into, I suppose.
If it slowed down on you,
Still the problem from last time?
Yes. I've done something to improve it, but it's still. I don't know. It still remains to be further investigated, I suppose. All right. I guess we also don't have to drag out the meeting if we're finished with our presentation and don't have any further comments. With that said, I guess do you guys have any further things to discuss, questions or comments?
No.
Okay. Well, thanks everyone for coming. If you're interested, definitely give the implementation a try. Check out the DDPG continuous action.py or DDPG2 continuous action.py. Our preliminary experiments show that they have no significant difference in their performance. DDPG2 continuous actions basically have the normalization on the environment that is used in PPO. But in our experiments, they don't seem to improve the performance of the agents that much. So for simplicity, if you want to experiment, definitely just use DDPG continuous action.py. And yeah, the core logic to optimize the model is the same, and just give it a try. Try to implement those three things: the clip double Q learning. What's the second one? The target network. Actually, target network is already implemented. The only thing that you're gonna have to change. Let me see. The only thing that you have to change is kind of adding the tmod n over here, as well as implementing the target action smoothing over here. Over here somewhere. Right, because you're generating, and also the minimum of the Q values, which should be over here. Right. Right. Where's the target? Yeah, the target is over here. The target should correspond to these two lines. And then you just do a tmod n over here. And then among other things, like basically adding two target critics networks. And then similar code could be found in Software Critic, where you can find how we implemented two different Q functions. But yeah, otherwise, I think that's basically TD3. All right. Thank you everyone for coming. Hope you guys have a good weekend. Stay safe, and if you have any questions, please don't hesitate to post it in the Slack channel, and we can discuss it and come up with some sort of resolution. And yeah, thanks for coming, and I'll see you next week then.
Thank you. Bye bye.
Thank you.
Yeah, thank you. Bye.